Welcome back everyone. In this lecture we will see a proof of Weyl character formula. So let us state the statement. So recall we have the following notation. So for lambda dominant, so we define S lambda plus rho to be the Weyl sum sine of sigma e power sigma lambda plus rho. Sigma varies over the Weyl group. Recall the Weyl group is nothing but Sn plus 1. So now with this notation, what is the Weyl character formula? So Weyl character formula says, if I take the character of the irreducible representation, so chi lambda, recall this is the character of V of lambda. So then it is given by this ratio of these two elements, S lambda plus rho divided by S lambda. So this can be viewed as identity in Z bracket lambda. So this is what Weyl character formula says. So we will actually prove the Weyl character formula using the Fradenthal's formula. So first let us recall some of the results that will be needed in the proof. So recall that we have defined this Laplacian operator from Q bracket of lambda to Q double bracket of lambda. Okay. So the Laplacian is defined from the formal power series ring Q bracket double bracket of lambda to Q double bracket of lambda. So this is given by L of e power gamma is norm gamma square e power gamma for all gamma n of lambda, and then you extend this to the entire formal power series ring. So now with this definition, so we have the following lemma. So this is very easy to prove. So I will just recall. So L of Fg is indeed given by F times L of G plus L of F times G plus twice the bilinear form bracket Fg for all Fg inside your Q bracket double bracket of lambda. So this is the relation we have between the brackets and the Laplacian operator. So this is something we know already. So now given this, we already proved this important fact. So if you are interested in proving this Weyl character formula, so that says this is supposed to be S rho. So chi lambda times S rho is same as S lambda plus rho. So this Weyl character formula can be written as S rho times chi lambda equal to S lambda plus rho. So if this is true, if and only if we can show that the S rho chi lambda is an eigen vector for the Laplacian with the eigenvalue norm lambda plus rho square. So this is something we already know. So this is a fact. So which we already proved, S rho chi lambda equal to S lambda plus rho if and only if the Laplacian of S rho chi lambda is exactly given by the norm lambda plus rho square times S rho chi lambda. So this means S rho chi lambda is indeed a eigenvector for this Laplacian with the eigenvalue norm lambda plus rho square. So let us recall this. So this is something we already verified. If you take this S rho, which is the Weyl sum corresponding to the Weyl vector rho, then twice this S rho comma e power gamma for any gamma. So this is exactly equal to summation mu in lambda, the multiplicity lambda mu twice the bracket. So this is the formula that we get it for the chi lambda. So So, this is actually obtained from this formula for S rho comma e power gamma. So, let me write the formula for twice S rho comma chi lambda, that is equal to summation mu in lambda the multiplicity of mu in V lambda times twice S rho comma e power mu. So, now with this we already know that twice S rho comma e power mu. So, this is given very explicitly by this formula S rho times summation alpha in delta plus e power alpha plus 1 divided by e power alpha minus 1 times the inner product mu alpha times e power mu. So, now if you substitute this back to this equation, substitute. So, then we get the following formula. So, twice S rho comma chi lambda is nothing but summation S rho times mu in lambda summation alpha in delta plus times the multiplicity m lambda mu times this mu comma alpha times e power mu e power alpha plus 1 divided by e power alpha minus 1. So, this is the formula that we get for this bilinear form applied to S rho comma chi lambda. So, this is something we need it later. So, I will just state it here for the future use. So, chi lambda, so by definition this is going to be like, so recall, so chi lambda one way to write is summation the multiplicity lambda mu e power mu, where mu comes from lambda. So, this is one way to write. So, that is why we are actually getting this formula. Okay. So, now using all these formulas we are going to actually verify the Weyl character formula from the Freudenthal formula. For that purpose, let us recall what is the Freudenthal formula and then just modify it accordingly. So, let us recall the Freudenthal formula. So, this is given by the following formula. So, for again fix lambda in lambda plus and then mu in lambda. So, then we have the following formula, the norm lambda plus rho square minus norm rho square times the multiplicity lambda mu is equal to norm mu square plus the inner product mu 2 rho times this multiplicity lambda mu plus some term xi. So, which is given by twice summation alpha in delta plus summation I range from 1 to infinity mu plus I alpha alpha the inner product times the multiplicity lambda mu plus I alpha inside V of lambda. So, this is what the Freudenthal formula looks like. So, now we will take this formula and then we will massage it and then modify so that we can get this Weyl character formula. So, for that purpose what we will do first, first step is multiply both sides by e power mu and then sum over all mu in lambda. Okay, this is the step 1. So, step 1 is multiply both sides by e power mu and sum over all mu in capital lambda. So, then we get the following things. So, if you multiply by e power mu here and then if you sum it over all mu, then what you get here is the character chi lambda, and similarly in the first place you will get the character, the second place you will get this mu comma 2 rho times whatever that is there. So, let us write down very explicitly and then see what is happening. So, now the left hand side clearly becomes equal to, so the left hand side is equal to the norm lambda plus rho square minus norm rho square times chi lambda. So, that is what you get. So, what is there on the right side? So, let us label them as 1, 2 and 3. So, then it is clear that what 1 becomes. So, 1 is going to be summation norm mu square multiplicity of lambda mu e power mu, where mu runs over capital lambda. So, if you think about it in terms of the Laplacian, this is nothing but Laplacian of chi lambda. Now, what is about 2? So, 2 is going to be exactly equal to summation mu 2 rho times the multiplicity of mu in v lambda e power mu, where mu in capital lambda. So, now one can use this following expression of 2 rho to rewrite this sum. So, 2 rho is nothing but summation alpha in delta plus. So, if you use this, then you can actually rewrite this sum as following: summation mu in lambda alpha in delta plus, then it becomes mu comma alpha the multiplicity lambda mu e power mu. So, this is the simplification that we get for the second summation. For the third one, what we get, so the third one, let us call it xi. So, this is going to be exactly twice summation mu in lambda summation alpha in delta plus summation I range from 1 to infinity mu plus I alpha inner product with alpha the multiplicity lambda mu plus I alpha e power mu. So, this is what we get. So, now what we do, we just change the variable mu plus I alpha to mu. So, this is the change we want to make. So, we change this to mu. So, then this xi can be rewritten as follows. So, xi will be exactly twice summation mu lambda alpha in delta plus. Note that this change mu goes to mu minus I alpha, that does not change this capital lambda. So, because of that we get exactly this is I range from 1 to infinity mu comma alpha, and then you get this multiplicity here, multiplicity of mu inside lambda, then this e power should change because this mu you change to mu minus alpha. So, this becomes mu minus I alpha. So, this is what we get it by changing the variable mu to mu minus alpha. So, now one can actually rewrite this as follows. So, recall that if I take summation e power minus I alpha, I range from 1 to infinity. So, this is exactly equal to e power minus alpha times 1 plus e power minus alpha plus e power minus 2 alpha etcetera, which is exactly equal to e power minus alpha divided by 1 minus e power minus alpha. But if you rewrite this, then you can see that this is exactly equal to 1 divided by e power alpha minus 1. So, summation I range from 1 to infinity e power minus I alpha is given by 1 divided by e power alpha minus 1. So, if we actually use that in this expression, then you can see that this is exactly becomes twice summation mu in lambda summation alpha in delta plus. So, now mu alpha will be as it is, and then the multiplicity lambda mu will be there, and then e power mu will stay, but the summation I range from 1 to infinity e power minus I alpha will become this 1 divided by e power alpha minus 1. So, this is the expression that we get it for xi. So, now let us actually use this expression and then sum all this 1, 2 and 3. So, if you just sum all these 3, then what we get? So, we have to see that. So, 1 is nothing but L of chi lambda, and then the 2 is given by this. So, now you can see some similarity between 2 and 3. So, let us write it here. Okay. So, this is L of chi lambda. The second sum is nothing but summation mu in lambda, summation alpha in delta plus mu alpha m mu lambda e power mu. So, summation mu in lambda, summation alpha in delta plus mu alpha m lambda mu e power mu. So, this is the second sum. So, now if we take this xi, which is the third sum, then you can rewrite again this as twice summation mu in lambda, summation alpha in delta plus and whatever the term that we have. But note that so this e power mu coefficient you can collect together and then see what it is exactly. So, if you do that, this is exactly L of chi lambda. So, this thing you can add it with this. So, this is exactly gives you summation mu in lambda, summation alpha in delta plus, then mu alpha and the multiplicity of lambda mu comes as common terms and e power mu as well. So, these terms are all common. So, this mu alpha m lambda mu and e power mu. So, which is common everywhere. So, then 1 will contributed from 2 and then 2 divided by e power alpha minus 1 is contributed from the third term. So, you get 1 plus 1 twice divided by e power alpha minus 1. So, this term if you simplify you can see that. So, this is exactly equal to L of chi lambda summation mu in lambda summation alpha in delta plus. So, this term becomes e power alpha plus 1 divided by e power alpha minus 1. So, then this exactly gives you mu alpha m lambda mu e power mu times e power alpha plus 1 divided by e power alpha minus 1. So, this is the term that you are getting. So, this is the term that you are getting by adding those terms together. So, now if you put them all together, then we have the following identity, because the left hand side looks exactly norm lambda plus rho square minus norm rho square times S rho chi lambda, which is exactly equal to, okay, what we are going to do, we are going to multiply by S rho. So, let us do that later. So, let us write it chi lambda. So, this is the left hand term. The right hand term is exactly L of chi lambda plus summation mu in lambda summation alpha in delta plus mu alpha m lambda mu e power mu times e power alpha plus 1 divided by e power alpha minus 1. So, this is what we get. So, now multiply by S rho on both sides. So, then we get the following identity. So, you get exactly norm lambda plus rho square minus norm rho square times S rho chi lambda is exactly equal to S rho times L of chi lambda plus this term star. Okay. So, now this can be rewritten as follows: the norm lambda plus rho square times S rho chi lambda is equal to norm rho square S rho chi lambda plus S rho L of chi lambda and then plus this star term what we have here. So, now if you think about it, the L of S rho is given by norm rho square S rho. So, this is something we know. So, now using this we get we can replace this star again, okay. The norm lambda plus rho square S rho chi lambda, which is exactly equal to L of S rho times chi lambda plus S rho times L of chi lambda and the term the bigger expression star. So, now this you can see that this looks very closer to L of S rho chi lambda. So, to prove that the left hand side is exactly equal to L of S rho chi lambda. So, using this observation about L of F g. So, let us recall that I have written it in the very beginning. So, L of F g is given by F times L of g plus L of F times g plus twice this bilinear form F comma g bracket F g. So, to prove the term that we have here is exactly equal to L of S rho chi lambda. So, it is enough to prove that. So, you can see that already L of S rho chi lambda is there and then S rho L of chi lambda is there. So, this star term we need to prove it is exactly equal to twice the bracket S rho comma chi lambda. So, this is what we need to prove. But if you recall the identity that we have already have which I proved in the beginning using the formula that we established before. So, this twice S rho chi lambda is exactly given by S rho times the summation mu in capital lambda summation alpha in delta plus, where the coefficient is given by this mu alpha times m lambda mu e power mu times e power alpha plus 1 divided by e power alpha minus 1, which is the term exactly appears here on the on this star. So, we are going to multiply S rho with this star. So, this is what we get here. So, this is exactly this. So, that implies that the right hand side is indeed this. This is the right hand side. So, that proves that norm of lambda plus rho square S rho chi lambda is exactly given by the Laplacian applied on S rho chi lambda. So, this is what we wanted to prove. In order to prove S rho chi lambda is nothing but S lambda plus rho. So, which is actually true because of this. So, that proves that the Weyl character formula is true. So, this proves that chi lambda is exactly equal to S lambda plus rho divided by S rho. So, this is indeed a very interesting formula, and we can actually prove many interesting applications of this formula. So, we have this very powerful formula now. So, we can actually get many interesting applications about the irreducible representations, so and their multiplicities and so on. So, indeed what we are going to see as applications of this Weyl character formula, there are plenty of applications, but in this course given this limited time we are going to only see the following applications. As a first applications we will see the formula for the multiplicity given by constant. So, this is what called constant's multiplicity formula. So, then later we will actually play around with this Weyl character formula and then prove what is called Weyl dimension formula. So, this formula indeed tells you that what is the dimension of this given irreducible representation V lambda. So, this tells very explicitly dimension of V lambda in terms of lambda and the positive roots. So, now the third one, which is actually tells about the number of given irreducible model that occurs in the tensor product. So, which also called Littlewood Richardson coefficient, but we are not going to actually prove the Littlewood Richardson rule in this course. So, that multiplicity can be actually given in many different ways. So, the multiplicity formula that we are going to see is the Steinberg's formula. So, the Steinberg's multiplicity formula again very much a theoretical formula. So, that actually tells the following things. So, given lambda 1, lambda 2 in lambda plus, we can consider this V lambda 1 tensor V lambda 2. So, this is a finite dimensional representation for SLN plus 1. So, now using the complete reducibility, you can write this as direct sum of some V lambdas with some multiplicities n lambda. So, we can write it as direct sum of V lambdas with some multiplicity n lambda, where lambda runs over lambda plus. So, this n of lambda is what called the Littlewood Richardson coefficient in the tensor product, or this is also sometimes called multiplicity of V lambda inside this tensor product V lambda 1 tensor V lambda 2. So, basically it counts the number of times this V lambda occurs in the decomposition of V lambda 1 tensor V lambda 2. Okay. So, this number we want to actually compute most of the time, and that leads to some very interesting combinatorics. So, using the Weyl character formula, one can give some closed formula for this number. So, that is given by Steinberg's formula. Okay. So, at least I will actually do all these three immediate important applications, and then later I will actually tell about how to compute these characters of irreducible representations in terms of the semi-standard Young tableaus. So, given the limited time, I may not be able to prove that. So, maybe I will actually tell you very explicitly how the algorithm works, and then I will state the result. And later we will also see there is something called Littlewood Richardson rule, which is again a combinatorial rule that actually tells you that how to compute this Littlewood Richardson coefficients, which are this n of lambdas. So, that is the ultimately goal of this course. So, after that we will stop the course. Okay. So, we will continue with the applications of Weyl character formula in the next class. Thank you.